Okay, so today we're going to be talking about the scientific method and experimentation, or how to set up an experiment. So this is going to be a lot of definitions, so make sure you have your notebook out, ready to take those definitions, and if you have to pause the video because I'm moving too fast, go ahead, so you have extra time to write things down. So first thing I want to talk about is facts, hypothesis, laws, and theories. A lot of people get these terms mixed up. So I just want to kind of clarify what they are. Facts. Facts are simple, basic observations that have been shown to be true. It's things that you and I and almost anybody would not dispute just by walking around the room. For example, there are 5 trees in my yard. That's a fact because honestly, anybody could walk to my yard, look at it and go 1, 2, 3, 4, 5. Yep, there are 5 trees in your yard. We're good. Okay. Another fact would be that my shirt is red. Now, it is true that there are some colorblind people in the world who wouldn't be able to verify that right now, but they know that they're colorblind, and so most of those people would basically trust that if everybody says this is red, okay, it's probably red here. So a fact is something that has been shown to be true, nobody could argue about. Okay, it's some sort of observation. A hypothesis, on the other hand, is a proposed explanation or a prediction. This should be testable. You should be able to test a hypothesis. Now, sometimes in science we talk about what's called a null hypothesis. That is an alternative to the hypothesis. Right? So it's something that's proposed. You don't need evidence for a hypothesis. It's just a proposed explanation, prediction. So it's basically a guess. Right? So an example, if you drink coffee before going to bed, then it's going to take longer for you to fall asleep. That is a hypothesis. Until you actually go and do this little experiment and collect some observations and facts, then it's a hypothesis. You don't have anything to support this idea. A null hypothesis in this case would be if you drink coffee before going to bed, it's going to have no effect on the time it takes to fall asleep. It's an alternative to that hypothesis, kind of nullifying it. All right? So if you have a hypothesis, there would also be a null hypothesis, kind of the exact opposite, kind of implied, if you will. Now, a law. A law is a description, okay? A law is a description. It's often mathematical, a mathematical description, and it shows the relationship between 2 or more things of some sort of natural phenomenon. So laws simply describe the observation. They don't explain how they work or why they work. They're just, this is what happens. Okay, for example, Newton's law of gravity. Any particle of matter in the universe attracts any other with a force varying directly as the product of the masses and inversely as the square of the distance between them. That is a mathematical relationship. So Newton is describing how 2 objects in the universe are attracted to each other based on their mass and their distance from each other. Okay, and there's a mathematical formula for it. That is a law, right? Theories. Now, this is not a hypothesis, okay? A theory is an in-depth explanation of a natural phenomenon supported by a large body of evidence. This is the scientific way of saying theory, okay? Newton's law doesn't actually explain why 2 objects gravitate towards each other. It just explains how this object and this object gravitates towards each other based on their masses and their distance. It wasn't until 3 centuries later, after Newton, a long time later, Albert Einstein came up with the theory of relativity, and with a whole bunch of evidence supporting it, he was able to explain why these 2 bodies come together. And basically, they're bending space-time, and because they're bending space-time, they're falling in towards each other. It's complicated, but look it up on YouTube if you really want to learn about Einstein's theory of relativity. Okay, but it's an explanation of the law. Right? So, facts, hypotheses, laws, theories. Facts and observations are not the same thing as laws. Theories are not the same thing as a hypothesis. A theory is actually something that is quite solidly backed up by evidence, whereas a hypothesis is not. And theories and laws are completely different things. A law can't become a theory can't become a law. They're just 2 sides of the coin here. Right? So the scientific process, the way it works, we start with observations or noticing something or having a question about it. We form a hypothesis. Then we either do some experiments and revise our hypothesis or kind of go back and forth around here, maybe go back to the observations. We jump around a lot. But if we do some experiments and we learn some things, and we have data now to back those things up, those things come into possible theory, sort of a working theory. And in this working theory, we do some more experiments, other people verify it. Eventually, what happens is this eventually becomes either a scientific law, meaning it's something we have observed happening a lot, so we know that this is going to happen pretty much all the time, or it becomes a scientific theory. It's an explanation supported by a lot of data of what we see. Okay? Scientific theory, scientific law. Data. Data is facts. Okay, it's observations. It's used to make and support a hypothesis. So this is what you'd be collecting in an experiment to support your hypothesis. Right? Once a hypothesis is well supported by lots and lots of facts, and it's not contradicted by any, then it can possibly be considered a theory or a law. Right? But you need the facts, you need the data to support it. Now there are two kinds of data, right? Qualitative data and quantitative data. Qualitative data is information that describes, all right? So color, odor, shape, or some other physical characteristic. It's a description. Earlier I said that my shirt is red. That is a qualitative data, right? In general, anything that's going to relate to the five senses, how something looks, feels, sounds, tastes, or smells, that is qualitative. It's a quality about it. Quantitative data, on the other hand, that's numerical information. It's numbers. It tells you how much, how little, how big, how tall, how fast. For example, it is 72 degrees in this room right now. That is a quantitative measurement, quantitative data. So any measurement of temperature, pressure, volume, mass, anything like that, where we get a number and a measurement, that is quantitative data. So two types of data. Now in an experiment, your goal is to collect data to either support or reject a hypothesis. So we have experiments here where we set up controlled observations where we're going to either collect qualitative or quantitative data to test this hypothesis to provide support for it. Okay, mostly experiments are about collecting appropriate data which supports the hypothesis or might actually show it to be null, a null hypothesis. So what is appropriate data in an experiment? Well, you want to basically leave no doubt that the data, the observations you are making are caused by whatever your idea is. Okay, so there's a couple of things that you have to have in an experiment in order to have a good experiment and to provide appropriate data. Okay, this is where I start to lose some people, so please pay very close attention to this. We have what's called an independent variable. Okay, that is the variable that is being controlled or manipulated by the scientists, by you. All right, the dependent variable, that is the variable that is going to change in response to what the independent variable did. All right. Then you have constants. Constants are carefully controlled variables that you make sure are kept the same to make sure that there's no change caused by those constants for the dependent or the independent variable, so that the dependent variable is only being affected by the independent variable. Now I know that was really, really confusing here, but let me give you sort of an example. Let's say you wanted to see whether or not plants needed sunlight to grow. Okay? Plants need sunlight to grow. That's kind of your hypothesis here. Okay? So, your independent variable is sunlight. You are going to control the sunlight. I'm going to take one plant and put it in the dark and one plant and put it in the sun. And then we're going to let them sit for a few weeks. All right? That is your independent variable of the thing you're controlling, sunlight. All right? Now your dependent variable, that is the thing that's going to change in response to the independent variable, in response to the sunlight. That is its growth. So I can measure how high they grow if they have sunlight and if they don't have sunlight. All right? Now, I know you guys understand the outcome of this, but bear with me here. In order to make sure that it is the sunlight that is causing it to grow or not grow, that dependent variable, the constants that we have, They have to be carefully controlled so that the only difference between those two plants is the sunlight. So I want to make sure that they are watered the same. I want to make sure that they have the same amount of soil, that the soil is the same. I want to make sure that the same type of plant. So everything else about the experiment needs to be exactly the same, constant, carefully controlled, everything else, just so that I know that if it doesn't grow very well, it's due to the lack of sunlight. My hypothesis here. If anything else is not the same between the two, it could be argued that might have been what caused it. For example, if I put fertilizer in one of them, well, maybe the fertilizer is what actually caused it to grow better, not the sunlight. We don't know because you didn't keep that the same between them. So, an independent variable causes the dependent variable, and then the constants, we want to make sure that everything else is exactly the same so that we know it is the independent variable that causes the dependent variable. Okay? All right, now, sometimes in an experiment, but not always, scientists will use a few different things. One of those is a control group. A control group is a group that's selected to represent whatever is normal for the situation in order to compare things to. For example, if you were to test and see whether a drug works, a new medication, you would want a control group where that group has the condition that you're trying to medicate, but you don't give them the medication, because that would be kind of what's normal here. You give one group the medication to see if it works, but you need a control group there in order to compare it to, like, what does it look like without the medication, so that we can be sure that it was the medication that caused them to get better if they get better, okay? And not something other thing that might have happened. Trials. Trials is when you do the experiment multiple times just to see if the results. Sorry, that slide is a little off there. Trials is when you do the experiment multiple times to see if the results repeat itself. Okay, so that should be repeat itself there. I'm sorry. Now, blind. Blind means that participants in whatever study you're doing, they don't know what variable is being changed. They don't know something about it, or they don't know if they are part of the control group or if they're part of the, say, the one that gets the medication. The reason why this is, why we have blind, is because we've noticed that if people think they're getting the medication, then that might actually affect their results for some strange reason. So we don't want the results to actually be affected by them knowing something about it. So a lot of times studies will be done blind, and they actually will even be done double blind. That means that the scientists themselves, they know what the variables are, but they don't necessarily know who's in what group. So in that drug trial that I keep referencing, if the scientists who are studying the people who have the drug and the people who didn't get the drug don't even know which ones have the drug and which ones don't have the drug, and the people who are taking it don't know, nobody knows except maybe some other person who's not even a part of this. They're just kind of holding the information there and be like, all right, when you're all done, here's who had what. That's called a double blind, and that makes sure that the scientists don't affect it, the people taking the drugs aren't affecting it, and we can be sure that with a double blind, that study is just the medication or not the medication. That's the whole point. It's another way to make a control. Okay? Now, I've got an example here, another example of an experiment. So let's say I want to do an experiment. I have a question. Does gender affect your ability to taste the difference between Pepsi and Coke? Okay, I have a question here. So I make a hypothesis. Girls can taste the difference between Pepsi and Coke better than boys. That's my hypothesis. I have nothing to support that, which is why it's a hypothesis. Okay? Maybe boys can taste it better than girls. Maybe the null hypothesis there, boys and girls can equally taste the difference between Pepsi and Coke. So, I mean, we have a hypothesis, we have a question. Let's do an experiment to see the result here. So my experiment, I set up, I select 50 students from my classes. Half of them are boys and half of them are girls. I let them taste test 2 cups of cola. I label them A and B. One of those is Pepsi and one of those is Coke. If I was doing this really, really well, I wouldn't know which one is Pepsi and which one is Coke. And they definitely don't know which is Pepsi and which one is Coke. So they have to figure it out and decide. So they taste it, both of them. Oh, this is Pepsi, this is Coke. Then we see who got it right, and we compare boys to girls to see which group can more accurately tell the difference. Now, in this experiment, what is the independent variable? What is the dependent variable? What are constants? What am I keeping constant and controlling here? Pause the video for a second and see if you can figure it out. Ready? So, my independent variable in this instance is gender. Okay? Boys versus girls. That's what I'm trying to compare here. My dependent variable is the ability to taste the difference between the two brands of cola. Now, once again, just to clarify, an independent variable causes the dependent variable. So, I'm saying that being a girl or being a boy affects your ability to taste the difference between the two brands of Coke. Independent variable, dependent variable. Okay? Constants that are in this case, things I'm trying to control for to make sure they're not affecting it. Tasted the same two brands. Everybody got Pepsi or Coke. They all got the same amount of drink in the cups. They all got 2 unmarked cups. I had equal amounts of boys and equal amounts of girls, 50 of them total, so 25 and 25. And I had tried to keep them about the same age since I picked students. I didn't have any of my teacher friends come in here and be a part of this experiment. So a couple of things there that I tried to make sure were the same so I know it's just the boys and girls that's affecting it. Now I actually did multiple trials here because since I had 50 students, that means I'm basically doing a boy-girl combination 25 times. So I had 25 different trials, and I can kind of see it's not just these two people, it's a whole group here. So I got more information, more accurate the more trials I do. Now conclusion here, judgment based on the information obtained. Okay, so if you form a conclusion, you look at the information that you got, the data, and then you come to a judgment. Right? That's a conclusion. Note that a hypothesis can never actually be proven. You can say that a hypothesis is supportive, give it a little thumbs up to that idea, and it might possibly be true. You get more and more evidence to support it, and it's more and more thumbs up. If, however, you find an evidence in a different situation that does not support it, then it has to be discarded. So you can disprove a hypothesis, but it's kind of weird. Even though you can disprove it, you can't really prove it. You just support it. Now, it's a weird thing to think, but you can only support an idea. You can't really prove an idea, but you can disprove it. Hope that was enlightening, and thank you for taking notes here.